Hi everybody, Dr. Pingle here. We are talking about the last portion of the assignment, which is running an ordinary least squares to generate a residuals analysis, and running a very simple trend analysis by doing a field calculation comparing 2 different years and seeing how the chlamydia rate has changed over time. Let's start with an ordinary least squares regression. These are exceptionally easy to run in ARC. You can find it in ordinary least squares. In this case, our input feature class is going to be our final spatial data set, which includes all of the counties and then all of the fields that we have been interested in. Our unique ID we'll just use as an object ID. That should work fine. This has to be an integer field. So anything that is an integer field that's not a FIPS code will work okay. Or actually, sorry, a FIPS code will work. It just has to be saved as an integer. So you could, for instance, cast or change a string or text-based FIPS code into a number. For a dependent variable, this is the variable that we're trying to explain. So in this case, we were trying to explain the Trump election data. So we'll take a look here at this. So what we'd like to explain, again, kind of going back to Richard Middleton's chart, is how the chlamydia rate affects the Trump vote. So if we're back here, that means that our dependent variable is the Trump vote. You'll notice that that doesn't show up on this list here, and the reason for that is that somehow our Trump vote has gotten turned into a text field. So I'm not exactly sure how or when that happened, but that is an easy thing to fix. We can just create a new field. And make sure that it's of a type that supports decimals. So in this case, we'll just use a float. Save that. And then calculate this field as being equal to this one. Looks like it looks like we've got a bad value in here that's throwing this off. So that explains what happened there. Let's just do a quick fix then the other way. I'm not sure how many of those values worked, but we're going to rerun this calculation here after we fix a data ingestion problem that didn't show up. It didn't crop up when we worked in Excel, but it's cropping up here. So this explains why this isn't working. We've got a value here. We'll just zero that out or empty it out, turn it into a null value or an empty value. And now we should be able to rerun our tool and get to the end. Perhaps not. So this empty value isn't working either. We'll just put in a value of 0 here for now, or better yet, null. Still does not like this value, so let's see if we can fix that. Okay, to make life easy on ourselves, we're just going to set this to -9999. Make sure that our values are saved. And then run this again. All right, great. Okay, so if we do a sort on this, we can hopefully find our bad value. We don't really want that hanging around. Okay, and now we can set that to null. Okay, so let's go back and try to run that OLS again. So our input feature class is the same. We're still using object ID. We'll stick this again into OLS results. Now our dependent variable, if we've done a good job here, should have a %trump float value, which we need. And then to explain that, we're going to try to use the chlamydia rate. So what this is doing is exactly what you were doing in Excel. It's essentially fitting a best line to this. In this case, it's a linear fit, and then we can look at the results. Now, if we look at these, we got an error here, so we'll see if we can figure this out. All right, we get a final estimate here, so we do get a fairly detailed report. So we can find things like the overall coefficients. We can see, so these are coefficients on each of the pieces here. This is a coefficient describing the relationship effectively. The probability of this is unlikely to be actually 0, and the reason that, even though this is a pretty small number, the reason that that's essentially 0 is that we have a very, very large sample size. If we open up the OLS results, we should be able to see how well it worked, if at all. We've got the %trump vote, we've got the chlamydia rate, but as it says, it didn't actually write out. In this case, it said we couldn't add the field estimated. I'm not exactly sure why that happened, so we'll have to dig in a little bit and try to figure that out. So one thing that may have gone wrong is that because we have missing data in here and here, the OLS just was non-functional for some reason. I think that's probably unlikely, but that's one possibility. The first thing that I'm going to do is just try to write this out to a different location. We'll see if that works. Okay, so this time it worked with warnings. Kind of working through these issues is fairly normal. Okay, so we've got our results that didn't work out, and we have our results that did. Here we're looking at the results that did. So you can essentially export this map as part of your assignment, but then you're going to need to explain what you're seeing. So let's talk about what we're seeing here. First of all, we have some missing values, so those are showing up as blank values. The kind of blue that you're looking at under here are actually values from the underlying data set. If we turn the topographic map off for just a second, we'll get a better sense of this. So one of the things that you could do before running this tool is to run fill missing values. So fill missing values is nice. We won't run it on this data set because I want to kind of keep things on the rails, but essentially what you can do is you can put in your input values and set the fields you want to replace or estimate missing values for. And you can select more than one field at a time, which is handy. You can set a variety of different fill methods, although average is almost always what you're going to be interested in, potentially the median. But then you also have to do the conceptualization of spatial relationships, which is what do I consider a neighbor? So contiguity, edges, corners is often a good bet. That's going to use all of the surrounding ones. As long as it's touching the county that you're trying to estimate, that'll work. So that's kind of how you would do it. There's a small bug in the data that was not going to let this happen, and it's a little bit far afield for this assignment. So we'll talk about fill missing values in detail in a future assignment. So what kind of patterns are you seeing here? Well, one of the things that we're looking at is a lot of the unexplained variance. And we talked about the scatter plot in Excel. We said that anything above the line, we draw a best fit line, and anything above that line is higher than you would expect given the relationship, and anything below the line is lower than you would expect given the relationship. And that's what we're looking at here. So based on our, if we sorry, if we're trying to explain this relationship between chlamydia and who votes for Trump, in some places the model works pretty well, and so those are essentially found in this kind of yellow mid-tone color. So you can sort of see where that model works and where it doesn't work are going to be designated by places that are far away from the line, indicated here by the standard deviation. How far away is that relative to the other residuals? So the dark blue here represents places where the values are essentially under predicted, places where this relationship doesn't work too much, and there's the estimates that you're getting are off on the low side. So you can see that there's a bit of a spatial pattern to that. It's not working very well in that way in the Northeast, and it's not working very well along the coast and in some parts here of kind of the West. Where is that model estimating high? Those are essentially going to be here. And again, the meaning for this goes something like, given the chlamydia rate, people are voting for Trump more than we would expect. Now, the chlamydia rate is not a very good predictor of the election, so that's why you see a lot of red and a lot of blue. It's not that hard for chlamydia rate to be wrong. If we used some other variable, probably population density would be a pretty reasonable variable. We would expect to see this pattern probably be a little bit different. But in this case, so these are places where the model is essentially predicting high. People are voting for Trump much more than their chlamydia rates would indicate. And on the coasts and in the Northeast, these are places where people are less likely to vote for Trump than their chlamydia rate would indicate. Okay, so that basically summarizes the residuals analysis. So your job would be to sort of not only run this tool, but then interpret the map that you're seeing. So let's talk about the second part, which is a temporal analysis. Okay, so for our temporal analysis, what we want to do is take a look at how one of these explanatory variables has changed over time. And in this case, we're looking at the chlamydia rate. We're using data from 2016, and so we could use the data from 2011 as kind of a far enough away point that maybe the signal is kind of stable. You can imagine that a one-year change might not be significant enough to be reliable. So we might want to use something a little bit more robust. So a 5-year period is probably not too bad. In class and lecture, we had talked about maybe more robust ways of doing this, and there are some tools in ARC that can also help you with temporal analysis. But for this particular analysis, I wanted to keep things kind of simple, and so we're just going to do a sort of a 5-year change calculation. So I've downloaded the 2011 data. I'm just opening it up. And rather than try to read this in here, what I'm going to do is just extract what I need. So I'm just going to pull out the FIPS code. And the chlamydia rate from 2011. Which is here. These aren't exactly the same numbers, or at least it's not labeled that way. But I think if you dig in the metadata, you'll see that this is essentially what they're reporting. So we'll pull these out. and delete that row. And we should be able to bring this in to our data set. Okay. Okay. Now we just need to do a join. We can remove the residuals analysis for now. We don't need that. And we're going to add a join. So we do want to be a little bit careful here, making sure we're using the right piece. We want to use a FIPS code over here. It doesn't really matter which one we use, but we'll use this lowercase one here since that's what we've used before. And then we're just going to double check to make sure that this came in the way we would expect. So you can see that the FIPS code is over here, and that FIPS code in fact did not come in correctly, so we're going to need to fix that. So here we're just using the same trick that we did before. We're just making sure that we're declaring this as a text field, pasting it as a value, and then we can delete these pieces and save this. We'll try saving this as a Excel file and see if that does the trick. Okay, so there's always maneuvering to make sure that the FIPS code is coming in correctly, but now we've got something that's definitely a text field, and we have our chlamydia rate. So now we can do the join. To FIPS2. All right, and I'm just going to export this again as a joined data set. Okay, that's done. can open the attribute table, and there we have our chlamydia rate from 2011. It is important to note that this has been recorded as an integer value. That doesn't make such a big difference, but knowing that these values have changed and sort of how they've been reported is a good thing to be aware of, at least. Okay, now we can do our final calculations on this. So what we need to do is add a field. So this is going to be the chlamydia rate increase. We need to make sure that we're saving this as a decimal enabled number. We can save that and then run our calculation. So our calculation is essentially going to be the 2016 rate, which is just the chlamydia rate here. And then from that, we're going to subtract this one. Essentially, that's going to give us a value such that if the rate has gone up, so like let's say the 2016 value is 100, the 2011 value, let's say was 90, we're going to get a positive 10 in there. So positive numbers are going to make sure that they are going to be places where the rate has gone up, and negative numbers are going to be places where it's gone down. If we switch those around, you'd have to be aware of that sign. Okay, so we're going to do just a quick symbolization here is all it's going to take to get a look at it. So we'll symbolize these with not graduated colors, but unclassed colors. And here's our chlamydia rate increase. We've got some bad values down here, so it's just always kind of good to keep an eye on that. We've also got some missing data, just like we had before, so this is more correct than what you're seeing there. One of the things that we could do is maybe symbolize this using a different color scheme. So when we have diverging data or data that's kind of centered around a zero value or a middle value, it helps to have a diverging color scheme to accompany it. So we'll just take a quick look through here to see if we can find one that we like. So any of these are functionally diverging, so we could pick something that looks like that, for instance. And there we would start to get a sense of our temporal increase. And we've essentially set our zero value, or we need to set our zero value such that these are symmetrical. So we want to try to ballpark this somewhere in the middle, or we could just type the values in. If we wanted to choose something that was going to be a little bit more continuous friendly, probably turning them all on wasn't a good idea. We could maybe use something like this, and then set our values here again so that they're more or less equal. An easier way to do that, I suppose, is to use graduated colors, in which case you can use breaks. But how you symbolize it is kind of up to you. Let's talk a little bit about the results. Let's change this back. So unfortunately, I don't know of a way to set this by typing the values in. I'm sure there's a way, but we're just going to ballpark this to make this more or less symmetrical, something like that. All right, so here our middle value is essentially a 0 value, indicating not much of an increase at all. Negative values are going to be places where the rate has gone down. So that's why this is color coded as green or good. These are going to be places where the rate has gone up. So you can see that in this case, sexual transmitted diseases or infections are kind of on the way down in a lot of places kind of in the south, which is good news. A lot of the rest is sort of mixed, but you can definitely pick out some sort of hot spots where the rate has been going up. If you wanted to take this a step further, for instance, you could look at how this trend impacts other variables, election results, or whatever, how it's related to population density. But that's not necessary at all for this assignment. Getting the work to this point is certainly far enough. So we talked about two things. One was the residuals analysis, so using the ordinary least squares tool to predict one variable or more than one variable, how it changes a response variable or a dependent variable. And then at the end here, we looked at how we could do a simple temporal analysis by using two time fields, subtracting one from another, and then seeing where those rates are going up or going down. So with that, we'll call this good. And if you have any questions, be sure to contact me. Thanks for listening. Bye.